Hello, everyone. So, I want to talk about system design, and in particularly, I want to mention some of the points that I think are important when creating a system, when designing a system, and I hope that these points will help you in your next interview or in your schoolwork. So, as I was reading the internet about architecture, I found this quote, and I think that this is probably one of the best quotes that I read. A perfection is achieved not when there's nothing left to add, but when there's nothing left to take away. To me, this means that you should design your systems to be as simple as possible without extra complexity. And especially in today's fast moving world where we move fast, break fast, simple systems that are not over engineered, that do exactly what they're supposed to do and nothing extra, are perfect. So to start off, I want to talk about my first point, which is single principal responsibility. And to me, this is probably one of the most important principles out there. Your service that you're designing, or it could be a class, it could be a function, should do only one thing. If it does one thing, later on it will make your life much easier when you want to add or modify things with this service or use this service as part of the different system. As long as it does one thing only, it will make your life in the future much, much easier. Your code will be much simpler, your tests will be much simpler, and the service can be reused by many different services later on. Another thing that I think also important, which builds on top of the first principle, is that you should isolate things that change from things that remain the same. So whenever you're building systems and if you build functions or you build endpoints or you build web services, if a web service does something very well, and of course it does one thing, something small, it is best to move it away and not touch it and build other services on top of that that use your service. So building on top of the single responsibility principle, building isolated services that do exactly one thing and moving them and not touching them later on will make your life much easier. Um, we as developers make bugs all the time, and once you get something working, it's great to not touch it and build services that would use um, whatever you built before. And if you have a service, if you work for a startup, and the startup has very fast moving business requirements, there are some pieces of your code that always stay the same, and it's always good to leave them unchanged and don't even make any pull request or repo. Don't touch the function, don't touch the class. If it works, it's best to leave it alone and build other utilities and tools that use it. When designing a system from scratch, and this is very helpful for the interviews, it's always good to talk about data first. This is my preference, and at the end of the day, whenever you build a system, what matters the most is the data. The data will tell the analysts, business analysts, and the business how your product is doing, and building data that building around the data is a good way to start. And when thinking about this, you should choose a right database as well as design a schema in a way that follows above principles. And of course, you should consider three different data stores. When designing a right schema, you should also remember that if you have a table that is less likely to change, it should probably be isolated. And if you have a table that you don't know what you're going to add to it, if you don't know if there's going to have an extra column, etc., it's better to keep tables that are less likely to change separate from the tables that are more likely to change. If you're going to write a migration for the table, if you're going to add extra columns or modify the table, it's better to uh, build in a way that you build a component, a very small component, course, following the single responsibility principle. You build a component, build a table, design a table, and if you don't touch it, that's perfect. You just build another table that would use that table later on. But as long as you follow the principle where tables that change will be in one place and tables that don't change will be in a different place, you'll have a better design. Later, another important point is that you should consider three databases or three data stores when thinking about your system or talking to an interviewer about what you're going to design for. And I think that's very important. So I think what your interviewer is looking from you, or what you should know in general, uh, the three data stores and what they're used for. And you would typically want to go with SQL, but that's not always the case. Each database has its own use cases. And I've seen candidates just point out that they have used SQL before and they should go for SQL always. And I had candidates that say otherwise. I have used NoSQL, MongoDB, and that's like solution for all. And I think that it all depends on the use case, and you should describe why each database is good for its use. SQL is great for structured data, but also the data that is transactional. What SQL guarantees, a lot of the SQL databases guarantee, is asset compliance, which means that once you write something to it, you're guaranteed to that the data will be there for sure. And that is especially important around payments. I have used third-party APIs that have used NoSQL database for transactions, and the cases I have seen is that NoSQL database, because it's a document store, it is um, it is scaled horizontally, and there's a bunch of different nodes. But once you write to one node and you read immediately, you're not guaranteed that the results will come back with the data. So you could issue two different statements to read or to write, for example, to a database, and followed by a read. And the read would return back a result that has been written by the first query, but not by the second. If you're dealing with payments, that is very dangerous. You could charge a customer twice. You could overcharge or undercharge. Or if you have a malicious user, they could take advantage of this. Uh, Basically, it's technically a feature of NoSQL. So NoSQL guarantees this. Uh, sorry, SQL guarantees that this will not happen. NoSQL does not guarantee. So you need to think about when using NoSQL. You can use it for things that it's typically good for unstructured data that doesn't really require this asset compliance. For example, you could use it to store a user profile, or if you have a time series or JSON blobs, of course structured ones, user settings, for example, if you're designing a video game, or if you're designing profile on Facebook, settings is a good big object that could be stored in a NoSQL database. SQL is more for structured data and the data that you need to you can query and make sure that when you write to it, the data will be there. And of course, the third one is in memory. We want to keep the in-memory store for temporarily in-memory objects. This is great for caching. I think you want to immediately mention Redis, for example, is the most popular one, and this is something good for temporary use. So caching is one example, but writing results and putting them in a Redis so for faster reads. Next time, like you can pre-compute something, put it in Redis. When user requests it, you'll go to Redis to fetch it back. And if you restart your in-memory data store, you lose this data, no problem. You can of course recompute it and put it back in there. And I think those are the three primary differences. Sorry, those are the differences between the three databases. And I think as long as you understand those differences, you'll do well, and your system design will be good. This one, building in layers. This is something that I have realized as a software engineer that everything we use is built on top of each other. If you use Mac, it's built on years of different macOS versions, which eventually go back to Unix days. And a lot of the components even in Ubuntu, in Linux, in Windows, in any operating system, are built on top of the other components that were built on top of the other components that were built on top of the other components, etc., until they reach core functionality. This kind of leads back to, again, single responsibility principle. Somebody built a very small component that works. People kept building on top of it, building on top of it. For example, if you code in JavaScript, Ruby, or Python, it's built on top of C++. That compiles down to assembly, that goes down to lower level um, zeros and ones eventually. So everything is in layers, and once something does really well, you just build on top of it. You don't modify the current thing. You build on top of it, and that's how you can scale very easy. So when you design a system, whether it's a table in a schema, whether it's application, web service, etc., build something small that does very minimal, isolate it put it in a like separate place, and build on top of it. Build other services that would use your service that does something very well, and etc. As soon as you will build a system with a lot of such small components that do one thing and they do it well, it's very easy at the end to get all these components and orchestrate them to build your application. So you can have this bunch of different functionalities, and once you have all the different functionalities that do something well, you compose your app. So building in layers is something that I follow myself.
So another important point I want to talk about is designing your system to be asynchronous. The problems right now that I see is that complex systems involve a lot of microservices. And all those microservices talk with each other via HTTP. So a client would make a request to some gateway. A gateway would make a request to first microservice. That first microservice would make a request to second service. Second service would make a request to third service, and then third service would possibly make a request to a third-party API. And now we have a chain of services that all have HTTP connections open, and they all wait for some third-party API to respond, and then the data goes back to the chain, back to the client. There's a few problems with this design. First of all, each service has a lot of connections open. So that's a lot of HTTP connections that are just hanging there, waiting for third-party API to respond. This could cause issues. For example, what if one of the services restarts? Or what if deployment happens? What if one of the services auto scales up and then it's auto scales down? It's kind of hard to control at this rate all those HTTP connections that are kept open. How can we shut them down without actually impacting the client? And the better way of doing this is making and designing your architecture to be asynchronous. I have seen a few ways of implementing asynchronous design. One of the ways is we have a service, and that service would, instead of holding the connection, it would respond immediately to the requester, telling the requester that I am processing the job, and here's the ID for the job that I'm processing. So the requester would post, or it would request another service, and it would get a response back immediately. Then we have a less than 1 second or a few milliseconds of response time, and then the service would then continue doing its job. Another approach I have seen is queue mechanism, and this is what I want to talk about next. I want to talk about the importance of queues first, and why I think most of the architectures should implement them. Queues allow us to scale. They allow us to control our rate at which we are talking to either internal service or a third-party API. For example, let's say you have a third-party API and they have a post endpoint that you can create a resource. Some of the problems I have seen that occur in actually in production is that we have a service that sends a request to a third-party API, and in a happy path that works, third-party API responds. What happens if the service starts to scale on our side? So a client would then send hundreds, maybe even thousands of requests to the third-party API, and now we have issue. The third-party API could start responding with either they would rate limit us, or they would just start timing out. So we essentially could DDoS our third-party API or internal service. Then I have seen cases where people implement retry logic, and you could, for example, send a retry to a third-party API as well if you get, let's say, a network timeout or some other network errors. And as a result, we also can end up in a place where we send out a bunch of retries all followed by each other, and our third-party API or our internal service are having issues. Queues allow us to scale and control the rate at which we send out those requests. So not all queues have all these features, but generally most of them do. And one of my favorite ones is, let's say you want to talk to third-party API. You would on a queue, you would implement ability for us to control at how many requests per second we can send out a request to a third-party API. If a request fails, we will then retry to process their item from the queue. And of course, if you retry, you should have exponential backup. Don't retry immediately. You can have infinite retries, but as long as you have exponential backup, you don't want to have infinite retries and not have exponential backup. That would be bad. And if the request still fails, let's say that you do have a bad payload, or maybe third-party API is down for a couple of hours, you want to investigate what happened. So it's important to have a dead letter queue where requests that or items that never succeeded, they go to some place where on-call engineer or somebody can investigate. So queues can help you scale, and you can easily control the queue size and rate at which the items are getting processed. And of course, if you have internal service that talks to another internal service, you can also have queue mechanism. One service, a client service, would queue up items, let's say post requests, and it would then the queue would then would start processing as the client gets more requests to queue up. Your queue grows, and this causes a slow service. Your entire system slowly degrades in time. So the requests are getting processed slower, but nothing breaks. You don't bring down any of your services just because you send out too many requests. Your queue grows, and then you can scale up your services as needed based on the queue size or number of requests that are getting processed. So client service would queue up items to be processed by the server, and the server would can also send responses. If it's an internal service, it can also talk to your other internal service back via same queue mechanism. And now you have two queues that are talking, that are basically are used in order to have two services talk to each other. And you are for sure know that if you get a lot of them requests or you need to scale, your queue scales, but your services don't break. And I want to quickly mention another point is that when you design your system, you should always think about how components can fail, and then you can design it to fail gracefully. So database could go down, third-party API could go down, services could go down, and your system should always fail gracefully, whether your queues gets filled up, whether your database goes down, and you can return meaningful error messages, and the client would gracefully handle them. Whatever it is, you should always fail gracefully.
I also want to talk about testing, and I can't stress enough the importance of it. You should always write unit tests for your code. You should always mention to your interviewer that everything will be tested in various different ways. Unit test means that you would write tests for all your functions, all your classes, and you should achieve 100% test coverage. That means you should, in your test, exercise all the paths that your code can take. And in your unit test, of course, if your code is interacting with a database or third-party API or other third-party dependency, you should always mock it out. Whether it's a database, you should mock out the database. Whether it's a third-party provider, you should always mock it out. There are various ways of mocking it out. I think a lot of the testing frameworks provide mocking, but you can also follow different design patterns, such as the driver pattern, and inject uh, different drivers, mock drivers that would essentially simulate what the code would do in production. Uh, Next is integration and end-to-end tests. You should always, when you complete your piece of code, when you deploy your application to your staging or sandbox or development environment, you should always have a test that would actually hit your endpoints, and those endpoints would actually interact with the database. They would interact with possibly either a mock third-party provider, or if a third-party provider has a sandbox or development environment, they should hit that. And this way, you can actually test that all your services are properly working with each other and with any third-party services. And finally, when you deploy something to production, you should always make sure that there's a smoke test that can ensure that your deployment went out fine. Lastly, I want to talk about monitoring and alerting. It's very important for your application to be healthy, and you want to make sure that it's healthy. This, you should always monitor different aspects of your application. You should monitor resources, such as whether CPU is high, memory or disk is low, um, whether your application is doing fine. You want to make sure that your application produces metrics, and these metrics ensure that your application is healthy. For example, do you have 1 million user signups in a few minutes, or do you have, if you deal with payments, do you have some sort of payment issue with payments where users are getting charged over in a loop, um, which could be very bad. And of course, if you have proper monitoring and metrics set up, you should set up alerts based on this. And if something goes off, your on-call person should get notification, and they should go and fix the issue or investigate the issue. So your team should have an on-call schedule where an engineer would do a rotation, and in a rotation, they would make sure that they watch out for any alerts that are incoming um, from production servers. This would include alerts that could happen even at night. And as on-call engineer would see an alert, they should investigate the issue and write down the results in a runbook. Um, for example, you could see that your CPU went high and your servers are becoming slow. And if it's 3 a.m., you would possibly restart the service. This would temporarily fix the issue. You would write down in a runbook what the on-call engineer should do in case they see this issue, and of course create a Jira ticket or issue in your tracker to later on investigate and fix the issue. But until this issue is fixed, we need a temporary solution, and this temporary solution would live in a runbook for on-call engineers to make sure their production servers keep running.
So that's it. I think if you learn these points and you understand them, you should do well on your interview or in your next time you design a system at school or work. And let me know if you agree or disagree with anything I mentioned, or if I missed something, I'll be happy to include it next time. Anyway, thanks everyone.